This tutorial video is basically going to contain all of the important information that I left out in the last two tutorial videos. I will include some clarifications and corrections that I need to make from those last said videos. The main reason I'm making this video is because the TESS mission has recently been extended for a fourth year and beyond, up to at least September 2022, so I want this tutorial to last. So without further ado, let's begin. One of the main things I really should have mentioned in the first video is that Planet Hunter's TESS is not permanently available to take part in. The data for each new sector comes around just under every month or so, and the usual rate for when an entire sector has been classified is roughly 2 weeks. So this essentially means that there's an extra 2-week interlude period where there's no data to be classified. To know how long a sector has left until it has been fully classified, we just scroll down the page until we see this progress bar. Currently, as it has only been a couple of days into Sector 32, only a couple of subjects have been completed, so it is at 0%. During the next few days and weeks, it'll eventually take up to 100%, where you'll eventually get a message up here in red stating that the workflow has been finished. And this is when you will know that you are in the interlude period. This period doesn't always last 2 weeks, and at best can only be a couple of days, but it is an average, so it usually depends on when the data is released and how fast the Planet Hunters team can get the data onto their system. The best way to check or at least predict when the data is coming is if we go to TESS's website under the observations section. We can see the current status of TESS, which we can see is currently scanning Sector 34. You can also see that Sector 33 has already been finished, so you can expect the data to be released relatively quickly after Sector 32 has been completed. We can also scroll all the way down. We can see the dates of when each TESS sector is being scanned. You can also see which area of the sky TESS is targeting for that selected sector. Another way to check if there's any data release notes for the sector you're expecting to classify. If these have been released and the sector is not yet on Planet Hunters, then you should expect that it will be very soon. And I'll place the links to both of these in the description below. The Planet Hunters team also sends emails stating that the data is ready to be classified, but sometimes they don't send these right when the data is fresh. Also, the best chance of finding planetary candidates is right at the start of a new sector, so it is worth checking these every now and then to get a head start. One thing that I glossed over in the first video is the importance of understanding the difference between U-shaped and V-shaped transits and what they mean. This here is a presentation from the Department of Astronomy in the University of Texas, and I think is perfect for explaining this. So here we have 3 types of transits that you should be aware of. You have your optimum transit in the middle of here, that moves perfectly across the center of the star. You have your suboptimum transits, which are essentially the same as optimum transits, but they're on the edge and tend to be harder to detect if the light curve is noisy, and tend to have shorter transit durations. And then you have your grazing transits, where only part of the object is transiting. In a perfect universe, optimum and suboptimum transits would be shaped like a valley, as you can see here, where the floor is when the object is transiting, and when the top is not, and where the slopes are when it is in phases in and out of transition. But this is not what we get when we measure other stars and transiting exoplanets. What we get is this distinct U-shaped transit, and this is due to an effect known as limb darkening. You can see in this image that the star's luminosity is not uniform, and this is the same for every other star. It is significantly dimmer closer to the edges of the star than it is in the center. So you can see the difficulty in spotting smaller planets for suboptimal transits, as the transit diff wouldn't be as deep as it was if it was an optimum transit, since it's blocking less light. And as you can see written here, knowledge of where the transiting object is precisely is difficult to determine due to not fully knowing where the limb darkening effect is on each and every star. So finding the true radius is a challenge, and there's usually a significant margin of error when this is calculated. V-shaped transits are produced by grazing transits, as you can see on this diagram here. They are shaped like a V because there is no point when the entire object is transiting the star. so they don't have a floor or a base on the light curve. The reason for why these are problematic is because only a portion of the object is transiting, so therefore it hides a significant portion of its radius. This here is a light curve that somebody linked to me recently, and it is hard to tell. You can see that there's a transit here at day 18. And this thing here is not a transit. This is due to an event known as a momentum dump, which I'll talk about in a bit. It is a V-shaped transit, which, if I bring this up using a third-party software, which I've zoomed in at the transit, you can see that it is distinctly V-shaped, as there's no floor or base to the transit, so it's distinctly V-shaped. So if we do the radius calculation, so 0.918, which is the solar radius, times the transit depth percentage, which is, I think it's roughly around 0.3, so yeah, 0.35, and you get a value of roughly 0.5 Jupiter radii. So the only thing we can determine is that this object is at the very least that size. There are ways to accurately calculate the radius from grazing transits, but it involves some relatively complex maths, and it's generally beyond the scope of planet hunters and my current understanding anyway. But I'll put some links in the description if you're interested. The main point, though, is that V-shaped transits are often suspected of being eclipsing binaries, so you should always be cautious when you're encountering them, and pay attention to the transit depth and, of course, the target star's radius when you're marking these on. Something that can be often mistaken for planetary transits are events that are known as momentum dumps. These are a result of when TESS uses its reaction wheel to correct its momentum from external forces. So the use of this is necessary to keep the spacecraft stable when it's taking measurements. The effect they produce can vary significantly, from no effect at all to a massive drop of brightness as you saw on the last curve. This one here is of a variable star. We can clearly see the points of when the momentum dumps occur. Now from afar it looks very tiny, and almost an insignificant drop. But what we didn't consider is the solar radius, which we can see is 73.870. So this is a really big star. And if we go to Sinbad, we find that this star is HD 11249, and that its spectral type is indicative of a red giant. So if we go back to the curve, you can clearly see that this drop in brightness here, which is roughly around a drop of 0.25%, this will probably be indicative of around an object the size, or 4 times the size of the Sun. So these drops can be very significant. To find out when the momentum dumps officially occur, go to the data release notes and select the sector you are classifying. And then you scroll down to page 9 by these numbers down here. So all the way down to page 9 until you see these two graphs. And you can see here with the graph zoomed in that you can see the vertical cyan colored lines and the assorted time on the x-axis. So this is something I suggest you check for before starting classifying a new sector, so you don't mistake planetary transits for these events. And to give you an example of one that really does look a planetary transit, we have this curve in sector 33, and you can see this transit here, which is at roughly day 19.4. But if we look at the data release notes for sector 33, which you can see is here, and you can see if you count along the x-axis, this eventually counts to roughly it corresponds to 19.4, this momentum dump. So it is likely that this transit here is due to that rather than actual planet transiting. So it's best to always keep an eye out for these. And while I have this light curve, I might as well show this animation down here, which shows why TESS has data gaps in the middle of the curve. So this shows TESS's orbit around Earth, and the blue portion of the orbit is when it's taking measurements, and this orange portion is when there's a data gap. This is because during the time when it's in this phase of the orbit, it points its antenna towards Earth, and it uploads all of its data to us. And as you can see what I've written down here, both momentum dumps and data gaps are unavoidable, and they're completely normal. So the best way to manage them is to simply know when they occur, so we don't mistake them for planetary transits or any other stellar phenomena. Sometimes when you're classifying these light curves, you may encounter a strange event similar to this light curve, where it looks like there's a transit and then it's followed up or preceded by a massive spike in brightness. That almost looks like a solar flare. But it's due to neither of these things, and it's caused by what is known as an SSO, or a solar system object. Commonly, these are often asteroids that move into the line of sight between TESS and the target star. From the dark side, it usually mimics that of a transit, and the light side, which is basically just a reflection of the sun's rays, which is significantly brighter than the target star being measured. So it mimics that of almost like a solar flare or almost a reverse transit, essentially. And since TESS is looking at a specific region of the sky at one time, a single SSO can show up on many different light curves in the same sector. So this is just another thing to look out for. So this is another light curve, and we have a transit-looking event at day 6. Though it's quite strongly V-shaped, but it still may have the potential to be planetary in nature. So if we scroll down, you can see that someone's already done the radius calculation, which is roughly 1.2 Jupiter radii. At the time, this one didn't have a TCE published, and it's not a TOI, but so far this looks promising. The next thing that planet hunters like to check is what is known as the background flux, which are essentially concurrent measurements with the target star's ones, but only that they measure the space around it rather than the star itself. Now, unfortunately, planet hunters doesn't have the means to check this background flux, so the only way you'll be able to check this background flux is to use a third-party software. And there are two pieces of software I recommend you use. There's the one that I use, which is LC Tools, or there's another one that if you know basic programming, which uses Python, which is Light Curve with a K, and which uses full frame images to get all the information that TESS is given. And links to both of those are in the description, though you will need to ask permission directly from the author of LC Tools, and then they will give you the link to the software if he chooses to. So this is the same light curve we were just looking at, with the Cadence spin at 30 points per hour, or in other words, basically one measurement for every 2 minutes. So when I press Shift B here, we get a second set of measurements in red, which represents the background flux. If I go down here and decrease the vertical zoom, which takes a while, you can see here there's a massive spike directly over our supposed transit. So what this means is basically the space around the target star suddenly got brighter at this point. Now the cause of this is likely due to an SSO passing in the field of view of TESS, but unlike what we saw previously, that it's not directly blocking the target star. So, and also light scattering can cause a similar effect to this as well. But the main effect that this produces is that since the surrounding space is suddenly brighter, it means that the measurements of the target star dim slightly, which then produces a dip that essentially mimics that of a planetary transit. So we can say for certain that this transit-like feature here is not due to a planet, but it transiting its star, and so therefore it's not a planetary candidate. You may also have a situation where the background flux decreases along with the potential transit. So this is when an object, typically a contaminating bright nearby star, suddenly becomes brighter than it normally is compared to the surrounding space for a brief moment of time, but the effect it produces is essentially the same, since it also slightly dims the target star being measured, so you also get this transient-like feature. But this one's also not a planetary candidate. And that's essentially all you need to know about the background flux. One way to check the light curve again after you've classified it without having to use third-party software is if you go to a website called MAST, or the Mikulski Archive for Space Telescopes. This is the central database upon where all of the test data gets uploaded to for the public domain to use, along with other readings from other space telescopes and instruments as well. And this is where projects like Planet Hunters acquire all their data from. And it's also the main site that ExoMAST is based on as well, given the similar names. Now, this is a rather complex site, but fortunately for us, we don't need to use much of it. The easiest way to get to MAST from Planet Hunters is if we go to the talk page of what the subject you are classifying, click the subject metadata button, and click the link to ExoFOP, and loads. And if we go down to external links down here, click that, and when it loads, this will essentially give you all the data that is available on this particular star. An alternative way is to just copy and paste the TIC ID into this search bar up here, and that will also bring you to this screen. To the left here, we have some very specific filter settings that you can check. So if we check the TESS under the mission filter, it'll only give us the results from TESS, which is what we want. To the right, we basically have a direct image of the star like we do on SIMPAD, but the field of view is larger, and you can basically change the length of how big you want it to basically cover the entire screen. And down here has its own assorted settings. If you click the cog button, and you can change the background survey. So for instance, I just changed it to the two mass background survey, which can be quite useful at detecting binary stars. But what we came here for is, if we get rid of this, is this data here. There are two sets of data here. We have full frame images, or FFIs, and then we have the light curves themselves. If there's lots of data here, we can narrow down the filter further. So if we go down to target name filter and check this ID rather than the TESS FFI, and it only gives us the light curves, which is what we want. You can tell which sector the light curves are from here by just looking at the observation IDs over here. So move this to the center a bit, and you can see here that we have one from sector 3 and one from sector 30. Some objects probably will just have a single sector of data. Others like this one can have just a few, and objects that the professional astronomers are usually interested in, they're often the ones that get observed the longest by TESS. So they could have well over a dozen sectors, so it does vary quite significantly. So let's click on this button that is a time series viewer, as you can see highlighted there. And it'll load up the light curve. It may take a while, as it says there. Now, what we actually have is two different light curves. We have the SAP flux curve, or the simple aperture photometry flux curve in blue down here. And we have the PDC SAP flux curve, or the pre-search data conditioning SAP flux curve, up here in yellow. The SAP flux curve is basically just the raw data from TESS with no editing done to it at all. Whereas the PDC SAP flux curve corrects for instrumental effects, such as if the curve was affected by scattered light or an error of some form for a significant period of time. And then the algorithm will tend to delete that part of the curve, and it'll get rid of some of the most extreme outliers, such as this measurement down here, and also tend to flatten the curve a bit. It also might be easier to look at if you have a dark mode on your browser, especially when you're trying to zoom in. But so if I do that, it's much easier to see because all the background's all white. So, but this is just my own personal preference. Now, Planet Hunters uses the PDC SAP flux curve for us to classify. So it is the yellow curve we typically is the one we want. So to highlight an area of the curve, you just left click and drag to wherever you want, and I'll highlight that area of the curve. The range options down here means you can extend or contract the X and Y axis, which is time and flux, to your liking. These options give us to show us grid lines, so you can, if you want to accurately measure parts of the curve, it's there for you. We've got a smooth factor, so it will smooth a curve to a significant degree. So if you want nice looking curves, that's the way to do it, and different styles of smoothness. And there's an option to phase fold the curve to the exact point which you wish. First, by typing, if we look at wherever you want to start the phase folding, so you want this at this grid line here, so you type in the epoch will be 3.982, and then the period is how many, just a period. So if we want it every 2 days, enable phase folding, and that will just phase fold the curve every 2 days. And then if you want to change the period, you can put the increment how much you want it to change by. So for instance, we're going to change it by 1 day, and then plus or minus will change it. So 3 days, 4 days, 5 days. And this is how much it will fold by on the point you want. It looks like a mess, but this is because we're not trying to phase fold proper transits, but this is the way how to do it. And a good candidate would have all of the transits aligned up together like you would see on ExoMAST, folded at a single point. Sometimes it can be worth checking the SAP curve to see if you see abnormally large data gaps that were generated from the conversion to PDC SAP to see why the data was deleted. Though PDC SAP is often good at correcting most errors, and in most cases you don't have to worry about it, it's still not a perfect algorithm and can sometimes delete legitimate data. On this example, you can see up here and down here in yellow, the curve that the Planet Hunters were shown when it was classifying. The transits here, given the depth and the star's radius, would be indicative of an object that is probably on the planet binary boundary on its own. So just that would have likely flagged us this object as a potential candidate for us. But if we scroll down, what actually happened is that the algorithm mistakenly thought that the primary transits of this eclipsing binary were due to an error of some form. So it actually deleted the transits. So we had no idea that this was an eclipsing binary until someone thankfully investigated the SAP curve to confirm that this was the case. So it is worth checking the raw data for similar cases like these. You may also encounter artifacts from the PDC SAP conversion from SAP. So this is the V-shaped transit we looked at earlier, but it turns out the transit was actually due to a processing error, as there was no such transit to begin with on the SAP curve. So the algorithm manufactured this transit. But this is very rare, and I think this is the only time we've actually seen this happen, but it is something to keep in mind. And that is essentially MAST in a nutshell. So this is a pretty useful website in my opinion. I'm now going to spend the next portion of the video essentially clarifying and correcting a few things in the last two tutorial videos, since it's been quite a while since I posted them, and I've learned a lot more since then. And some of the things I stated were outright wrong, so So let's start on that. At 1 minute 18 in the first tutorial, I said that so there's one dot for every 30 minutes, so optimally there'll be 48 measurements a day if everything's working perfectly. Yeah, this is wrong. I don't precisely know what the cadence is binned at for Planet Hunters, as they don't list it anywhere on their website. But I'm pretty sure it's binned at 6 points per hour, which essentially means there's a measurement for every 10 minutes rather than 30. So to put that into perspective, using LC tools, I can show you the difference between them. This was the curve we looked at earlier with the background flux spike. But the difference is that it's binned at 6 points per hour. Now, if we look at the Planet Hunters curve, you can see that the number of points on this transit is very similar to this one here, and the similar amount of points up in the noisy part of the curve. But if I load up the same curve, but Cadence binned at 2 points per hour, which is a measurement every 30 minutes, you can see there's a lot less measurements on the curve. If we compare it back to the Planet Hunters curve, you can see there's significantly less. So I don't know precisely why I said it was binned at 2 points per hour. I think I misread the observations page on TESS's website. At 6 minutes 22 in the first video, I stated that a body that's anything over than roughly 1.5 Jupiter radii is unlikely to be a planet. So this is also not entirely correct, though I still would use the 1.5 Jupiter radii figure as a general rule of thumb. But since we are working with the radius and not the mass of these objects, there's a significant overlap between what constitutes as a planet and as a star, as we don't have that important mass value to work with to do that for us. So it doesn't mean that everything over 1.5 Jupiter radii is a star and everything under that value is a planet. It means that the general trend is that most objects over 1.5 tend to be stars and that under tend to be planets. So it's essentially a soft boundary and not a hard one. To give you a couple of examples that break this trend, this one here is of Celt 9b. It has a Jupiter radii of 1.891, which is much higher than the 1.5 boundary. Now, I was initially completely dumbfounded as it showed all the traits of eclipsing binary with your secondary eclipses, very large radius, but it had already been confirmed to be a planet by the time I looked at this on Planet Hunters. And it essentially confused me to the point where I made this thread asking why it was a planet when other similar objects were completely written off. But there are three main things that are highlighted for why this is a planet and not a binary. First off is the obvious one, where the mass was measured using radial velocity, and the results given back giving us a value of 2.88 Jupiter masses, which comfortably puts this in the planetary range. The second thing is, if we scroll down, is that this object has almost perfect U-shaped transits. So the radius can be accurately measured, and we know that it is not grazing, unlike many other eclipsing binaries that have strong V-shaped transits. The third thing is that Celt 9 is a spectral type B star, which the surface temperature is in excess of 10,000 Kelvin. And Celt 9b orbits once every 36 hours, so it's extremely close to its parent star, and it's the hottest known exoplanet to date, with an equilibrium temperature of 4050 Kelvin. It is so hot that it actually produces its own secondary eclipses of its own. It's not because Celt 9b generates its own luminosity, but it reflects the heat absorbed from its star to make itself a luminous object. And that is why Celt 9b is a planet, not a binary. We can also go to the other end of the spectrum. The smallest star discovered so far is only just bigger than Saturn, with a Jupiter radius of 0.84, but it has the Jupiter mass of 85.2, which means it's just massive enough to not be a brown dwarf, and it's a really dense star. And to also put it into perspective, TRAPPIST-1 has a Jupiter radius of 1.2. So you can clearly see that this is a really blurry boundary, the 1.5 figure when it comes to radius. At 9 minutes 55 in the first video, when I'm talking about simulated curves, I just want to highlight that there's another way to check if the curve is simulated or not. So you go to the talk page, and you click the subject metadata button, and if the subject you're classifying does not have a TIC ID, then the curve is simulated. I thought I'd highlight this point because there's often a new and optimistic and excited planet hunter that thinks they found a planet and goes on to share it with everyone, and then it's really disheartening when someone, and often myself, just has to cut them down by telling them that the planet they thought they found isn't real, as it has no TIC ID. And I was guilty of doing this as well when I was new as well. So I thought I'd just say that. At 1458 in the first video, I never actually mentioned that most objects do not have a TCE for ExoMAST. So if I go to ExoMAST, just type in a random TIC ID, just like 4678336, whatever, and press search, it will come up in yellow saying there's no planet found. Recently, there's been an issue where ExoMAST seems to publish the TCEs really late, often well after that sector has been fully classified. So it may not mean that there isn't a TCE generated for the subject you're classifying, but it does take a while now to look at them, and planet hunters are often using this less often than they were when I made my original videos. Around a minute later, at 1550 in the video, I stated that, and here is how long, well, roughly how long the star has been observed for. This is also wrong. So if I go and go to ExoMAST and with a completely different flagged candidate, what this is it's a data coverage plot that shows how much observations that have been done on the potential candidate by different telescopes during its orbit, and it's essentially a data filter. So it shows how much of the body's orbit consists of a transit here, and how much of it consists of Eclipse, which is here. Down here is all the associated data for this TIC object that is on MAST, so we don't have to track the data down over there. And so if I click on this TESS bar here, it'll just only filter and give me all of the data that's associated with TESS. So that's just essentially what that is. And at 1647, I still have no idea what this plot is supposed to be or what it represents. So if you do know what this means, then don't hesitate to comment so I can put it in the description. And finally, at minute 25:37 for the first video, when looking at the observing notes on TOI-1408 on ExoFOP, I thought I'd just clarify that they're just using the TESS telescope to use the radial velocity method, which is another way of detecting exoplanets, which measures the star's wobble, which can then give us a potential mass value for the planet. And using both the transit and the radial velocity methods then can give us more details, such as the potential density of the planet and if the planet's mass is like close to a brown dwarf or not. And as of the release of this video, TOI-1408 is still an active planet candidate and is yet to be officially confirmed, but it's still looking pretty good. At minute 15:04 in the second video, I stated for eclipsing binaries that because it's so big, it produces a an effect when it goes behind its star and it manages to reduce the brightness of it to a not as massive as a normal transit event, but it still makes its a mark on the light curve. Now, most of that was correct, but what wasn't was stating that the secondary eclipses were produced purely based on its size, which is not true, because they're produced by the hiding of the luminosity of the binary component. So if I go to this light curve here, I can show you this diagram. Basically, what is being measured for normal levels is the brightness of both components up here, which is this noisy part here. But when the smaller component moves in front of the target star, this is when you produce your primary transits. But as the smaller component is also generating its own brightness, when it moves behind the main component, the luminosity of the smaller component is then hidden from view, and that is how you get your secondary eclipses. The only way you can get secondary eclipses from a planet is if you have a similar situation to that of Kelt 9b, where you have a very large radius, a very hot star, and the planet is orbiting very close to that very hot star, and then which then would make the planet very hot and therefore luminous. But that is it. So in almost every occasion you see secondary eclipses, you are looking at a binary star. And the last thing for the whole of the stellar phenomena section, the ones that are highlighted are not the only types of stellar variability that you'll see, but they are the ones that you often encounter the most. If you want to see all the different types of stellar variability, then if you go to the VXX website, and if you go down here and click on variability types, and here you have a massive list of all of them. And they're being categorized into their assorted sections with small but accurate descriptions stating the features exhibited by them for each of them. Some stars may show traits of multiple types of these. So some you only find once ever on Planet Hunters, but if you're stuck at the type of variability you're looking at, then I suggest you have a read of all of these at your own time to find out which one is the one you need. So hopefully that is officially everything you need to know when you're planet hunting. I might do a similar follow-up video to that of the second tutorial, where I go through something like 100 light curves, classifying them all. But unlike that video, I'll be purely focused on the classifying, so I won't talk about certain concepts unless they appear in front of me at that time. So I hope you all learned something from this tutorial, and thanks for your time.